Welcome to Biogas Basics. My name is Jürgen Kube, and this is the first part of a mini-series about the gas system of a biogas plant. The first part will focus on the basics, the difference between reference and operational conditions, how biogas should flow through a plant, and the importance of the pressure gradient. I will identify the optimal way for connecting digesters in the gas phase and show a method for calculating the pressure profile over a biogas plant. We start with the reference state of gas. Every time a gas volume flow or a gas yield is mentioned, a reference condition should be stated as well. So, when we say a feedstock makes 200 cubic meters of biogas per ton, it implies that the 200 cubic meters are at a certain pressure, temperature, and humidity. Common reference states are 0 degrees Celsius, 1 atmosphere, that is 1.01325 bar, also referred to as norm cubic meters, 15 degrees Celsius, 1 atmosphere, called a standard cubic meter, 0 degrees Celsius, 1 bar, which is referred to as standard pressure and temperature, or STP, and 20 degrees Celsius and 1 bar, called normal temperature and pressure, or NTP. Norm cubic meters are typically used in Western Europe, standard cubic meters in the UK, STP is the current IBU-PAC definition, and NTP is used by NIST in North America. According to IUPAC rules, units should not be indexed, but in AD, nobody cares, and indexes before and after the cubic meters are common in AD literature. All reference states mentioned here use dry gas, but there are also reference states that use defined humidities. Make sure that everybody is on the same page regarding reference states when starting a biogas project. For international projects, check the local reference state. Here is a conversion table, based on ideal gas law, for the 4 states listed here. If gas yields are overpredicted by 5%, revenues from the AD plant will also be overpredicted by 5%. A 5% overprediction of revenues can be a 100% overprediction of profit, so this really matters. When we refer to a volume at a reference state, we are actually referring to a molar flow of gas. The temperature and pressure change over the biogas plant, but the molar flow of dry biogas remains constant. The calorific value of biogas or methane is also given at a reference state. Methane has a heat of combustion of minus 891 kilojoules per mole at 25 degrees Celsius, 1 bar. 3 significant digits is about the accuracy to which a calorific value can be measured. Most standards define calorific values with more digits, but these numbers are definitions, not measurements. The calorific value is given as upper or lower calorific value, also called gross and net, or superior and inferior calorific value. For the lower calorific value, all reaction products are in the vapor form. The upper calorific value includes the heat of condensation of water, so water leaves the combustion as a liquid. Efficiencies of CHPs or internal combustion engines are typically stated related to the lower calorific value. In the biomethane or renewable natural gas market, the upper calorific value is typically used. Converting from one reference state to another must consider the change of enthalpy of the products and adducts and the change of the density or compressibility factor of the fuel gas. All this makes converting calorific values from one reference state to another quite difficult. Conversions are only valid to 2 significant digits. Preferably, look up the calorific values from the respective standards. Here are calorific values for methane, propane and propene from the European EN 437 standard. Now let's go back to the impact of humidity. While gas yields are generally given at a reference state, for example in norm cubic meters, 0 degrees Celsius, 1.013 bar, dry, the gas in the digesters has a different temperature, pressure and humidity. The impact of the pressure on the biogas density is very low as a biogas plant typically operates around ambient pressure. Temperature has a higher impact, as biogas can heat up in the headspace of digesters, especially under dark gas domes when the sun is shining. Biogas is produced in the form of dissolved gas, which then forms microbubbles in the aqueous phase and finally accumulates in the headspace of the digester. It is saturated with water vapor. The water vapor content can take up a significant amount of the volume of biogas. The vapor pressure curve can be fitted with the Antoine equation for the required temperature range from water vapor tables or from NIST webbook. The Antoine equation is P equals exponential function of A minus B over C plus T. It is an empirical function and must be fitted to the correct pressure and temperature units. For the temperature range, 5 to 55 degrees Celsius, the parameters A equals 9.5793, B equals 2789.639, and C equals 189 degrees Celsius can be used. The pressure is in bar. The water vapor content of the wet biogas can be described with Raoult's law. The water vapor fraction is the water vapor pressure over the absolute pressure. Because the relative humidity is 100%, the water vapor pressure is the saturation pressure. The ratio of volume of humid biogas under operational conditions to the volume of dry biogas under standardized conditions can be expressed with the following formula. The volume of humid gas under operational condition over the volume of dry gas at reference conditions is reference pressure over absolute pressure minus water vapor pressure times temperature over reference temperature. Let's calculate an example. A biogas stream of 1000 norm cubic meters per hour flows from a secondary digester covered with a dark gas dome. The sun is shining, and the gas under the gas dome heats up to 55 degrees Celsius. The absolute pressure is 5 millibars over ambient pressure, 1.018 bar absolute pressure. The methane content is 55%. First, we calculate the water saturation pressure with the Antoine equation. It is 0.156 bar. That means that according to Raoult's law, around 15% of the volume in the gas phase is filled with water vapor. Next, we apply the formula to calculate the ratio between the gas volume under operational conditions to the volume at reference conditions. It is 141% in our example. This means that the 1000 norm cubic meters per hour flowing from the digester become 1410 cubic meters per hour under operational conditions. This number must be used to calculate the pressure drop in gas pipes, design blowers, and pressure relief valves and assess the storage capacity of gas domes. For example, a gas dome with a storage capacity of 3000 cubic meters can store the gas production of 2 hours 7 minutes, not of 3 hours. We can calculate the gas density with the ideal gas law. Generally, the density is pressure times molar mass over gas constant and temperature. For dry biogas at reference conditions, we can calculate a reference density. It is 1.26 kilograms per norm cubic meter. The formula for the humid density needs to be modified slightly. It is water vapor partial pressure times molar mass of water plus absolute pressure minus water partial pressure times average molar mass of biogas over gas constant and temperature. In this formula, we do not use reference pressure and temperature, but the actual pressure and temperature. The operational density is around 1 kilogram per cubic meter. This number is used for pressure drop calculations and assessment of flammable gases on site. What is the best way to connect the gas domes when designing a biogas plant? Here's an example biogas plant comprising 3 tanks. A primary digester that is fed with feedstocks and produces 80% of the biogas. A secondary digester that receives the effluent of the primary digester and produces 15%. And a storage tank that makes 5% of the total biogas production. One way to connect the digesters in the gas system is to run pipes from the primary to the secondary, from the secondary digester to the storage tank, and from the storage tank to the gas consumers. In our example, 800 cubic meters per hour flow from the primary to the secondary, 950 cubic meters per hour flow from the secondary digester to the storage tank, and 1000 cubic meters per hour flow from the storage tank to the gas consumers. This type of connection has many advantages. If there's a change in the quality of the produced biogas, the quality at the inlet to the gas consumers will happen gradually. For example, if the biogas plant makes a biogas with 50% methane and glycerin is fed, the quality of the produced biogas in the primary digester will jump almost instantaneously to 58%. This gas will flow in and out of the gas headspace in the primary digester, from there into the secondary digester, from there to the storage tank. The methane content at the inlet of the gas consumers will change slowly over days. Typically, the primary digester is the hottest reactor and the following reactor steps are colder, especially the storage tanks, which normally are not insulated. The gas will cool down as well, losing condensate and increasing its density, which saves power in the gas conditioning unit. If air or oxygen is dosed into the biogas, it must only be dosed into the primary digester. From there, the oxygen will flow into the secondary digester and storage tank. O2 dosing into the gas phase is a cheap way of desulfurization. H2S is oxidized to elemental sulphur and sulfuric acid. There are some downsides to this method, and it is not suitable for all AD plants. But if it is done, O2 is added in overstoichiometric amounts, meaning that it will not be consumed in significant amounts in the desulfurization process. The desulfurization will not run out of O2 in downstream reactors. O2 is also required for the H2S polishing step with activated carbon filters. I will do a presentation of desulfurization in the future. Generally, the connection of tanks in series often requires only short gas pipes that can stay above ground and do not require pipe gantries. The pipe connection will be comparably cheap. There are also downsides to this type of connection. The serial connection of digesters creates a high pressure gradient over the plant. Why is this problematic? Gas roofs, especially single or double membrane gas domes, have a maximal operational pressure. The pressure of a double membrane gas dome is produced by an air blower and a pressure control valve. The higher the operational pressure, the more expensive the gas dome will become. There is also a lower pressure limit of a gas dome. The internal pressure is required to create stability against wind and snow loads. If the pressure drops below 2 millibars, the gas dome will become unstable in high winds and can be damaged. The pressure gradient of the biogas plant is the difference between the highest and lowest pressure in the plant. It is limited by the operational pressure of the gas dome, or the set pressure of the pressure relief valves, and the minimal pressure that is required for structural stability. Connecting the tanks in series creates a large pressure gradient. So, this type of connection can sometimes lead to venting, especially if the gas domes are not rated to a high pressure. A second disadvantage is that a digester cannot be bypassed. If, for example, the secondary digester is offline for maintenance, gas cannot flow from the primary digester to the gas consumers. Alternatively, the tanks can be connected in parallel. Advantages and disadvantages flip compared to the serial connection. The pressure gradient decreases over the plant. All digesters are connected to one header pipe, which carries the gas to the consumers. The pressure drop in a pipe depends on the square of the volume flow, as we will see later. Because the flow out of the secondary digester and storage tank is very small, the pressure drop in the pipe is very low and the pressure in the respective tanks is mostly the pressure in the header pipe. Bypassing a digester is easy. Simply valve off the respective digester and the other tanks can continue to flow gas to the gas consumers. The parallel connection has many disadvantages. The gas quality can change abruptly. In this configuration, the system does not have to operate in a steady state, where gas from all three tanks flows into the header pipe at a constant rate and mixing ratio. Gas domes can store and discharge gas, which can reduce or even reverse the outflowing biogas stream. For example, if the volume of gas stored in the gas dome on the secondary digester increases with a rate of 300 cubic meters per hour, no gas will flow out of the secondary, and the gas to the gas consumers will be a mixture of 650 cubic meters per hour from the primary digester and 50 cubic meters per hour from the storage tank. The quality of the biogas at the inlet of the gas consumers changes. This can cause issues with some gas consumers, especially CHPs, which can start knocking when the CV of the fuel gas changes quickly. If oxygen is dosed only into the primary digester, the gas produced in the secondary digester and storage tank will not be desulfurized at all. Adding air or O2 into a tank with low gas production can be tricky, as the oxygen can accumulate in a tank with little outflow. Gas analyzers are notoriously unreliable and should not be used as a safety measure to prevent overaccumulation of oxygen. I will do a presentation about measurements on biogas plants. If the tanks are connected in parallel, the gas pipes will be longer and more expensive. They will also produce more condensate, and condensate removal pots might be required. Parallel and configuration in series can be combined to eliminate some of the disadvantages. A hybrid system has a low pressure gradient. Generally, the more gas pipes are in a plant, the better, and a single tank can always be bypassed. O2 can be dosed only into the primary digester, and some of the O2-enriched gas will flow into the secondary digester and storage tank. Changes in the gas quality will move faster through the system compared to a pure serial system. The biggest disadvantage is the requirement for a pipe gantry, long gas pipes, and condensate removal in the pipe system. However, there is a way to connect tanks that offers almost only advantages: the ring system. For this, we will need to look at the plant from the top view. We can connect the primary to the secondary digester and to the storage tank, and the secondary digester and storage tank to a common pipeline and withdraw the gas through a T-junction in the connecting pipeline. Gas can flow from the primary via the secondary digester or via the storage tank to the gas consumer. The flow will split, so that the pressure drop along all possible pathways will be the same. It will always go through one other tank to smooth out changes in gas quality. The gas cools down as it flows through the system. Oxygen must only be added to the primary digester. The connecting gas pipes are short and do not require condensate removal. And finally, a single tank can always be bypassed. The only disadvantage can be a reduced maintenance access in the middle of the plant, if the digesters are moved too close to each other, but this can be addressed in the design phase of the plant. I would recommend this type of gas system for all new build projects if possible. it is the most preferable way to connect tanks in the gas system. We can also invert the question. What is the worst way of connecting the tanks? The worst way is to connect the gas storage as a dead leg. Gas flows directly from the primary digester to the gas consumer. Only excess gas flows upstream into a gas storage. This configuration has a low pressure gradient in steady state because the flow from the storage tank to the secondary and from there to the primary digester is very low. But if the gas consumers are switched off, the pressure gradient reverses and widens, as gas will now flow upstream towards the storage tank. In normal operation, most of the gas will flow straight from the primary digester to the gas consumers. The gas will be hot and creates lots of condensate. Changes in the gas quality will immediately reach the gas consumers, especially when the primary digester has a rigid roof with a low headspace volume. The gas in the storage tank will stay there for a long time and can show high H2S concentrations. Generally, this configuration should be avoided. I talked about pressure gradient and pressure drops. How is the pressure drop between two biogas digesters calculated? We use the formula of Darcy and Weisbach. The pressure drop is half the density times the square of the velocity in the pipe times a friction factor term for fittings, elbows, valves, T-junctions, in and outflows into tanks or confusers and diffusers, plus the length of the pipe over its diameter times the friction factor for the pipe flow lambda. Technically, this formula is only for incompressible flow, but the changes of the biogas density are very small. Typically, the biogas pressure is slightly above ambient pressure, around 1000 millibars, and the pressure drop is a couple of millibars, so the density barely changes. The formula also assumes isothermal flow and no condensation or even two-phase flow. The density of the gas can be calculated with the ideal gas formula. Make sure not to forget the water vapor content. The friction factor of a rough pipe can be calculated with Colebrook and White. The formula for the friction factor is iterative. Start with the left formula and then insert the previous iteration into the right formula for 3 times. The formula quickly converges to a solution. We can assume rough pipes with a roughness of 1 mm. There will be all kinds of biofilms and puddles of water in the pipe that create additional resistances for the biogas flow. Biogas pipes are not smooth, at least not for long. Experience shows that the pressure drop of a biogas pipe is always underestimated. In reality, the pressure drop will be considerably higher than predicted in an Excel sheet. Do not focus too much on fancy pressure drop formula, for example for two-phase flow, but try to understand the dependencies instead. For an incompressible, isothermal turbulent flow with constant friction factor, the pressure drop is proportional to the square of the volume flow over the inner diameter of the pipe to the power of 5. Doubling the volume flow will quadruple the pressure drop. Halving the pipe diameter will increase the pressure drop by 2 to the 5th power, which is 32. So, make the pipes big enough. Larger pipes do not give diminishing, but power law returns. One reason why pressure drops are almost always underestimated are sulfur precipitations in gas pipes. H2S will react with oxygen and water to elemental sulfur, sulfuric acid and biomass. A biofilm forms at the inner pipe surface, and it will be stabilized by elemental sulfur. The biofilm has an uneven surface. It creates local peaks and troughs, and the troughs will accumulate water. The reduction of diameter, the uneven surface, and the moving water surfaces will all add to the friction factor of the biogas flow, increasing its pressure drop in the pipe. Oxygen is often added for desulfurization, but even if it is not added deliberately, it can diffuse over the gas holder membranes or can be introduced by the feedstock. So, the gas lines will experience fouling over time. Make them big enough. I will use this AED plant to explain how to design a ring gas system. The plant was built in the early 2010s in Germany. It has 2 CHPs providing high temperature heat via a thermal oil system to a nearby amine scrubber and peak electricity power to the grid. The plant is an excellent example of making full use of the potential of biogas. The client insisted on the color. The feed hoppers are in the building to the right. The plant has a primary digester, seen here in the middle, with a concrete roof and vertical paddle mixes. Its effluent is pumped into the secondary digester, which is the tank on the left with the cladding and gas dome. Liquid digestate is stored in 2 storage tanks in the background. They are not insulated. From the top, the plant looks like this. The primary digester has 3 biogas outflows, to the secondary digester and to each storage tank. Biogas can flow from the secondary digester to the storage tank 1. Storage tank 1 and 2 are connected via a short gas pipe, which has a T-junction where the gas can flow to the gas conditioning unit and then further to the gas consumers. All gas pipes are above ground and no condensate removal is required within the AD plant. We can assume that 85% of the gas is produced in the primary and 15% are produced in the secondary digester. The average biogas production is 1000 norm cubic meters per hour, but the plant has a variable gas uptake between 0 and 1380 norm cubic meters when both CHP are active. We will focus on the steady state here, where the biogas consumption is equal to the biogas production. The gas system is shown as a block diagram comprising a network of gas pipes and nodes. To calculate all flows and pressures, we use the following method. First, we define the gas production and the gas uptake or discharge for every node. Gas storages can store or discharge gas if the system is not in a steady state. The number of nodes is n. N is 5 in this example. The primary and secondary digester, the 2 storage tanks, and the T-junction from which the gas flows to the gas consumers. Second, we define the pipe length and diameter for every pipe. The total number of pipes is m. In our example, m equals 7. Most of the pipes are quite small, dn 200 or 8 inch. Only the last 2 pipes to the T-junction are dn 300 or 12 inch. Then we estimate a flow in each pipe and define a direction of the flow. The estimate does not have to be accurate, even the flow can point in the wrong direction. We then calculate the pressure drop in each pipe based on the estimated flow. We can simplify the pressure drop calculation by pulling all constant parameters into a constant K, which is multiplied with the square of the flow in the pipe to get the pressure drop. The formula for the pressure drop is the constant K times the square of the volume flow times the sine function of the volume flow. The square of the volume flow is always a positive number, even if the flow reverses and becomes negative. The sine function ensures that the pressure drop becomes negative as well in this case. The friction factor of the pipe does change slightly with the flow, but the changes are small and can be ignored for this purpose. Now, for all n nodes, balance the in- and outgoing biogas streams, the biogas production, and any stored and discharged volume flows. If the flow estimate is correct, the balances around all nodes will be 0. We are looking for m flows or independent variables. The balance around the nodes gives up n equations. The remaining m minus n equations are generated by identifying m minus n linear independent loops and adding up the pressure drop along the loop. Count pressure drops against the flow direction as negative. Vary all flows so that n balance equations around the nodes and the pressure drops in the m minus n loops add up to 0. Use the Excel solver for complex gas systems. Finally, we can calculate the pressure in each node by defining the pressure in one node and then calculate all other pressures relative to this node from the pressure drop. In this example, I express all pressures relative to the pressure at the T-junction, which is set to 0. The method used here is similar to Kirchhoff's circuit laws in electric engineering. Pressure is the potential and the volume flow is the equivalent to the electric current. Here is how it looks in Excel. The properties of biogas, viscosity, density, ratio of volumes under operational to reference condition, here 1.3, and the roughness of the gas pipes are given. The next table shows the 5 nodes, their gas production, the volume flow balance, and the pressure in each node based on the flow estimates. The flow estimates are in the next table. For each of the 7 pipes, I list flow at reference condition, pipe diameter and length, the constant K that contains all information about the flow resistance in the pipe and the pressure drop in the pipe based on the flow estimates. I balance flows in the reference state, but use the volume flow at operational conditions to calculate the pressure drop. Lastly, we have the pressure drop of the 2 loops. Let's quickly go through the formulae. Stop the presentation if necessary. We start with the balance of node 1, the primary digester. It is the gas production of the primary digester minus the 3 outgoing streams, from node 1 to node 2, 3, and 4. The secondary digester has a gas production, an inflow from node 1 and an outflow to node 3. Storage tank 1 has no gas production but inflows from node 1 and 2 and an outflow to node 5. Storage tank 2 has an inflow from node 1 and an outflow to node 5. The T-junction has inflows from node 3 and 4 and an outflow to the gas consumers. We see that most of the balance equations are not fulfilled and the volume balances of in- and outgoing flows around a node do not add up when the initial flow estimate is used. The pressures in each node can be calculated as follows. We set the pressure in node 5 to 0, but we can also choose any other value here. The pressure in node 4 is the pressure in node 5 plus the pressure drop in the pipeline between node 4 and 5. The pressure in node 3 is the pressure in node 5 plus the pressure drop in the pipeline between node 3 and 5. The pressure in node 2 is the pressure in node 3 plus the pressure drop in the pipeline from node 2 to 3. And finally, the pressure in node 1 is the pressure in node 3 plus the pressure drop in the pipe between node 1 and 3. When all the balances are fulfilled, we can construct the pressure in each node from every possible pathway. If the balances are not fulfilled, the pressures are not correct, no matter what pathway is chosen. The first loop is from node 1 to 2 to 3 and back to 1. From node 1 to 2 and 2 to 3, we count in the direction of the flow. From node 3 to 1, we count against the direction of the flow with a negative pressure drop. The second loop goes from node 1 to 3 to 5 to 4 back to 1. From 1 to 3 and 3 to 5, we count pressure drops in the direction of the flow. From 5 to 4 and 4 to 1, we count against the direction of the flow and the pressure drops are negative. With the estimated flows, the pressure drop along the loops is not zero. Now the aim is to vary the 7 flows here shown in red, so that the 5 balance equations around the nodes and the 2 balance equations around the loops, here shown in yellow, will become zero. We can use the Excel solver for this problem. We pick one of the constraint equations, here the pressure in loop 2, and square it, so it will be always positive and multiply it with a large number, here 1000. This is our target function. We now call the solver and minimize the target function by varying the 7 flows, so that the 6 remaining constraints become zero. Uncheck the Make Unconstrained Variables Non-Negative box and run the solver. Minimizing the square of one equality constraint is more stable than making a target function zero. Here are the results. All constraints are zero, and we have the flows and pressures in the system. Here is the pressure gradient over the plant, relative to the pressure at the T-junction. Despite using mostly DN200 pipes, the difference between minimal and maximal pressure is only half a millibar. The plant has gas domes rated to 5 millibar, so we can set the pressure in the gas domes to 4.5 to 5 millibar and the stability of the gas roofs is guaranteed. When double membrane gas domes are connected on a biogas plant, they will start to interact, and I will discuss this behavior later in this mini-series. But for now I will conclude the first part. Make sure to use the correct reference state when designing a biogas plant and its gas system. Humid warm gas in the gas system occupies more space than dry biogas at reference conditions. 1 cubic meter of dry biogas at reference condition can easily become 1.3 to 1.4 cubic meter of humid biogas under operational conditions, depending on the reference state and the temperature of the gas in the gas system. Blowers, pipes, and pressure relief valves must be designed for the flow at operational conditions. Undersized pipes, valves, and blowers are a common mistake on biogas plants when this volume expansion is ignored. The gas system of digesters can be connected in series, in parallel, in a hybrid mode, or as a ring system. This impacts pipe lengths, the pressure gradient over the plant, the transient behavior of the gas quality after changes in the feedstock, and the ability to bypass a digester. The preferable solution is a ring system, which has short pipes, low pressure gradients, and reacts slow to changes in gas quality. The only possible downside is restricted maintenance access for pumps and mixers if the tanks are moved too close together, but this can be engineered out in the design phase. The pressure drop of a pipe depends on the square of the volume flow and the pipe diameter to the power of -5. Doubling the flow quadruples the pressure drop, and halving the pipe diameter increases the pressure drop by a factor of 32, so make the pipes big enough. Generally, pressure drops are almost always underestimated because of two-phase flow from condensate and sulphur buildup on the inside of gas pipes. I showed a method to calculate the flows and pressures in a ring system. When biogas can flow from A to B along different pathways, the flow will split in a way that the pressure drop along all routes is equal. I showed the effectiveness of this gas system with an Excel example. That concludes the first part of this mini-series about the gas system of biogas plants. Designing the gas system is no rocket science, and this presentation lacks theoretical depth and focuses more on application know-how, but mistakes in gas systems are surprisingly common in AED plants. The next part of this mini-series focuses on what happens before, in, and after the gas conditioning unit. I hope you learned something new, and I see you in the next presentation of Biogas Basics.